In this special episode of Maker Mondays, we will be building this 3-wheeled rover that is remotely controlled with a DualShock 4 PlayStation controller. We will initially have a quick hardware breakdown, followed by a demonstration of how to use the libraries used within this project, and perform some quick analysis and break down the final project code. Now onto the hardware that we're dealing with here. First of all, we're going to be using the Raspberry Pi Model 4B, paired with an SD card pre-flashed with the Raspberry Pi OS. We will also be using a multi-half bridge circuit provided by Infineon, in particular the TLE94112 Pi Hat, to control the hardware side of the rover. For the human side of controlling the rover, we will be using a DualShock 4 PlayStation controller. And for the rover skeleton, we will be using this 3-wheeled, pre-built Lego set. Now technically anything could be used for such a project. You can use an old car that doesn't work anymore and just change the motors. You can use a fan like this one. You can use anything. Any just DC motor is going to do the job. Now let's take a quick look at the Raspberry Pi Hat itself. As you can see, installing it on top of the Raspberry Pi is a fairly simple process. The next step would be to connect the hat to power and to the DC motors. For power, it's recommended to connect it between a range of 5.5 to 20 volts, and for that you can always use an external power source, but to keep this project as simple as possible, we will use the Raspberry Pi's GPIO pins to power it. Before connecting the Pi Hat to our Lego set, we will connect it first to the simple DC motor fan and try to break down the code on a simple scale. First of all, we have to take care of the hat's power connections. This pin on the Raspberry Pi provides a 5-volt terminal, and this is ground. We will connect the ground pin to the slot with a negative symbol, and then we will connect the 5-volt pin to the slot with a positive symbol. We then connect the DC fan wires to the motor slots 1 and 5. Now that we already have a basic setup assembled and ready to go, let's hop onto the software side. Now onto the Raspberry Pi itself, you should make sure that you have the package manager for Python 3 installed. Do this by simply typing in a command line sudo apt install python 3 pip. Afterwards, install the Infineon multi-half bridge circuit library by typing sudo pip3 install multi-half bridge. Finally, for our last installation, we will install the Pi PS4 library by typing sudo pip3 install Pi PS4 controller. Now that we've got all the essentials installed, let's start diving into some action. Initially, we will clone the multi-half bridge repository. We do this by typing git clone and the link of the repository. Now let's navigate to the examples folder and execute the basic test. Once we're in the destination folder, which should be called examples_pi, we execute the script by typing sudo python3 basic test. As you can see, something's happening at our hardware setup. The fan has started to turn, which means that the motor is now being powered. Let's look at the code itself. Feel free to use Nano or Genie or whatever environment you like. I'm personally more comfortable with Studio Code. To begin with, the library module that we've installed already is imported. Next, a controller structure is instantiated. Thereafter, a motor structure is instantiated under this controller structure. The motor controller is enabled through the begin function, and the error registers which are used for debugging purposes are cleared using the clear errors function. The connections between the motor and the hat are specified through the connect function, where we also indicate to the program which connection do we intend to use as high side or low side. I personally don't give this much thought because I could always control the direction of the DC motor, so just keep in mind to have a connection on high side and the other on low. We could then set a pulse width modulation channel for the motor. You could also not use pulse width modulation if you do not need by specifying that in the set PWM function. In this particular example file, PWM is not utilized in the control of the motor. However, if we were to change that in the set PWM function, we would change the TLE no PWM to, for example, TLE_PWM1. We then enable the motor using the begin function. It is worth mentioning that you have to run the begin function for the controller before you do any form of motor configuration, i.e. before specifying the motor's connections or PWM utilization. And now, for the MVP of this script, there is the start function, which is the function that actually runs the motor. If you're using pulse width modulation, then you have the capacity to load the motor between the range of 0 to 255. Let's call this range the duty cycle range, where 0 is the motor not running at all, and 255 is full power. To change the direction of the motor, all you have to do is add a negative sign right before the number. In this particular code, the motor runs at full power for 3 seconds and then it is coasted. Motor coasting is when the motor is released without driving or active braking. From this little code snippet, we could get out that the code is dispersed into two main parts: skeleton and control. The skeleton is essentially the part where we tell the software how the hardware is set up, and the control part is the part where we are actively telling the motors exactly how we want them to behave. The active part mainly consists of the following functions: start, stop, coast, ramp speed, set speed. We've already covered start and coast, so let's have a look at the others. Let's start with stop. Stop is essentially a stricter form of coast, where we are actively braking the motor to stop it. Stop takes an input that indicates the braking force. The maximum here is 255. Next, we have ramp speed. This function allows us to gradually change the motor speed over a specific amount of time. We can either speed up or speed down. Ramp speed takes two inputs, the duty cycle range and the time in milliseconds. Let's say you're driving a motor on a duty cycle range of 64 and want to accelerate to 255 over 3 seconds. You do this by calling ramp speed and giving the inputs 255 and 3000. Finally, we have set speed. This function is equivalent to start, however it's intended to be used when the motor is already running. Set speed takes in a number within the range of 0 to 255. Now that we've become experts with DC motor control, the next step is to do the same with the programming of the PlayStation 4 controller. But before that, we would have to pair the controller with our Pi. There's actually a variety of ways to do this, either through command line or the GUI. To maintain simplicity here, we will do it through the GUI. To do that, first put the controller in pairing mode by simply holding the PlayStation button and the share button at the same time. Keep holding until the LED at the back of the controller starts blinking. Now onto the Pi itself, head to the right corner and left click on the Bluetooth icon. Click on Add Device and scroll through the list until you find the controller. Click on it and pair. Now you're connected. Now that we're all paired and ready, let's take a look into how we could use the DualShock 4 controller from a software perspective. On the module's GitHub repository, we could find a Hello World code snippet where we could print Hello World by pressing the X button and print Goodbye World by releasing it. All we have to do is copy that exact same code snippet and in the specified class add whatever event you want to use. Whether it's pressing the square button, releasing the up arrow, or even moving the analog sticks, everything is possible. In the repository, you could also find a list of events that you could essentially just copy-paste into your code. So now that our software background is fully in check, I'll just run a quick speed up of hooking up the Lego set with the 3 motors to the Raspberry Pi with the Pi hat mounted on top. A good upgrade to the setup is to use a small power bank to ensure portability. Coincidentally, this small power bank fits perfectly within the Lego set itself. This is it, the moment we've all been waiting for. It's time to program our rover. Let's start with importing the modules, and then running our Pi hat skeleton code. It's essentially the exact same code as the one from the basic test. Initially, we'll instantiate a controller, and since we have 3 motors, we'll have to create 3 motor instances. I'll call them motor 1, 2, and 3. Before we could specify the connections of the motors and whether we could use pulse width modulation or not, we will have to enable the controller using the begin function, and then clear errors. Now that that's out of the way, let's specify each motor's connections. I do not intend on using pulse width modulation, but in case I change my mind in the future, I will assign each motor a pulse width modulation channel. We then enable each motor via the begin function, and ta-da! Now the skeleton is done. Now that the skeleton is over with, let's get into the control part. To keep the code clean and simple, I'll define each intended task into a function. For example, in my setup, to move the rover forward, only 2 motors would run and they would run with full power in opposite directions. To make the code more readable, I'll put the 2 respective motor start functions into one move forward function. I'll do the exact same thing with coasting, stopping, turning, rotating, and translational motion. This part of the code is fully customizable to what functionality you want from your setup. Now that we're done with the motor control part, it's time to use the functions we just wrote with the controller code. I will just copy the Hello World code snippet from the GitHub repository and add the events I want and the responses that I would like to be associated with them. Additionally, you could also change the amount of time that the program would wait for the controller to connect to the Raspberry Pi by changing the value of the timeout. In my case, 60 seconds was absolutely fine. I always recommend testing the code with every little change you make to it, and not just waiting until you're done with the whole project's code, just to ensure that you avoid any big-time errors, and that the controls you assign are optimum to your liking. After revisiting my childhood fantasies while testing the code, it's time to set the final stone, which is to make our Raspberry Pi run our Python script on startup. In a command line, type sudo nano etc profile and scroll down until you find the end of the code, and then write sudo python3 and then the location of your Pi script. Then press Ctrl O plus Enter to save and then Ctrl X to exit. And voila! Now you're ready to roam the streets and show some driving skills. I hope you enjoyed this project and hopefully I see you again in other ones. In the meantime, drive safe.